All right, welcome to our practice final review. So we're going to go over these questions together. Find the mean and standard deviation for the given sample data, and round your answer to one more decimal than is present in the original set. All right, that kind of goes way back to when we first started. So what we do is we enter our values into a list. So go to Stat, Edit, and put in your numbers over here: 18, 18, 14, 11, 8, 8, 10, 17, and 12. Okay. Then we're going to do the one-var stats. So we go to Stat, Calc, click on one-var stats. Our list is in L1. Our frequency list is blank, and we go and calculate. So we're trying to find our X bar, which is our mean. So that's 12.88. So rounded to one decimal would be 12.9. And then our standard deviation, we're going to use the sample standard deviation, is 4.04. So if we're rounding it to one decimal, that's 4. Then it says construct a box plot for the given data. Include values of the 5-number summary in all box plots. Okay, so our 5-number summary is our minimum, our Q1, our median, our Q3, and then our maximum. Okay, and our numbers are sorted here. We are going to use our table function again. We could find, the minimum obviously is the smallest number. The maximum is the largest number. It looks like these are all sorted from smallest to greatest. And then you find the median is in the middle. But we can also just put it into a table. So we're going to put it into list 1. So I'm going to clear out list 1 first. Enter in all the data. We could put it as a frequency distribution, but I'm just going to enter all these values over here. 5.5, 5.7, 5.8, 5.9, 6.1, 6.1, 6.3, 6.4, 6.5, 6.6, 6.7, 6.7, another 6.7, then we have 6.9, 7.0, 7.0, 7.1, 7.2, 7.2, 7.4, 7.5, 7.7, another 7.7, 7.8, 8.0, 8.1, 8.1, 8.3, and 8.7. Okay, so it looks like I have 20, is that right? 29 values. I wonder, let me go through my list just to check. So 87, 8.3, 8.1, 8.1, 8.0, 7.8, then I have 1, 2 7.7s, I have a 7.5, a 7.4, 7.2, 7.2, 7.1, 7, another 7, and a third 7. Okay, it looks like I'm short one number over here. 6.9, 6.7, 6.7, 6.7, 6.6. So it's always a good idea to go through your list and check, because I left out one number over here, so I'm just going to enter it on the bottom, because it doesn't matter since we're just going to calculate the summary stats. Oh, so it looks like I forgot a 7.0, so let me enter that in on the bottom. I could sort it if I wanted. It would put it into the right place, but it doesn't really matter, because when I do my one-var stats, it is going to calculate these and put them in order for me. So go to Stat, Calc, one-var stats. We're using list 1, and we're calculating our summary stats. Okay, so what we want to do is go down, arrow down to the 5-number summary. So the minimum is 5.5. My Q1 is 6.4. Put it over here. My median is 7. My Q3 is 7.7, and my maximum is 8.7. So that's my 5-number summary. What percentage of babies have a weight below 7 pounds? Well, 7 is my median, so I would have to say half of my data. 50% is less than the median. And, obviously, if you just looked at the numbers here, your percentage would be slightly different. But it says construct a box plot. Really important, you want to scale it first. You don't want to scale it after. So our lowest number is 5.5. So let's say we have 5.5 here. We have 6, 6.5, 7, 7.5, 8, 8.5. So you want to have a consistent scale. So you draw your scale first. Our minimum is where the whisker starts. Our Q1 is where our box starts. The box goes from Q1 to Q3. So it's 7.7. And then the maximum is the whisker goes up to my maximum. My median is going to be a line right over here. So here's my box plot, and that's it. So it doesn't look like there's any outliers over here, and so on. Okay, let's look at number 3. You plan to make a survey of 200 people. The plan is to talk to every 10th person coming out of the school library. Is there a problem with your plan? Well, you're trying to randomize it in some way by going with a systematic sample and selecting every 10th person, but you're just standing in a convenient place, so this makes it a convenient sample, which is always a bias sample. So that's the problem over here. We don't have a random sampling method. Okay, what's the probability of an event that is certain to occur? Well, if it's certain to occur, that means it happens for sure, and the probability of that is equal to 1. If P of A is 2 and 19, find the probability of the complement. Well, the probability of the complement is 1 minus the probability of A, and that's 1 minus 2 19th, which is 17 over 19. So that's pretty simple. Your probability and the complement just add up to 1. So whether it's a fraction like over here or a decimal number, it's very simple to find the answer for that. Moving on to number 6 over here, some more probability. A 6-sided die is rolled. Find the probability of 3 or 5. This is the probability in one roll, so we have the outcomes 1, 2, 3, 4, 5, or 6. The 3 or 5 would be the desired outcomes. We always do the desired divided by the total possibilities. So there's 2 divided by 6, or the probability is 1/3. Next question. A bin contains 72 light bulbs, of which 10 are defective. If 5 light bulbs are randomly selected from the bin with replacement, find the probability that all the bulbs selected are good ones. Okay, so we have 72, 10 of them are defective, so we have 62 good ones. We're going to pick with replacement. So what we have is 62 divided by 72, right? That's the probability of picking a good one. Since we are replacing it, our numbers stay the same. So we're going to multiply it times 62 over 72, and we're going to do that 5 times. Our numbers stay the same. We have independent probabilities because we're doing with replacement over here. So that's 62 divided by 72 to the 5th power. And let's see what that is. 62 divided by 72. All that to the power of 5, and the probability is 0.473 over here. And it says round to the nearest 1,000. Okay, so that's what we did. 3 decimals. Okay, number 8, find the area of the shaded region. The graph depicts the standard normal distribution with mean 0 and standard deviation 1. So we have a standard normal distribution. The area underneath the curve, when we have z-scores given, we're using normal CDF. We're going to start with the z-score where our area begins, which is 0.59, and we're going to end up with a z-score that's a very large value, so we can use 10,000, and then our mean is 0, our standard deviation is 1. So normal CDF, so second vars, normal CDF, starting at 0.59. It looks like, it's pretty close to 50%, maybe 40%, something like that. Let's see what it is. A little less than that. So it's 0.2775, or rounded up to 76. So 0.2776. This is a probability. It's an area which is rounded to 4 decimals. Number 9. Test the indicated claim about the means of two populations. Assume that the two samples are independent simple random samples selected from normally distributed populations. So those are some of the requirements we need in order to do our test, to assume that the population standard deviations are equal. A researcher wishes to determine whether people with high blood pressure can reduce their blood pressure measured in mmHg by following a particular diet. Use a significance level of 0.01, that's our alpha, to test the claim that the treatment group is from a population with a smaller mean than the control group. Okay, so we're comparing means. So for the population, that would be mu1 is less than mu2. We're comparing two populations, and these are two different groups. We have a treatment group, a control group. These are independent samples. We don't have like a matched pair design. We have independent groups. So what that is a 2-sample t-test. It's a t-test because we do not know what the standard deviation is, and so we have a 2-sample t-test. Okay, so we're going to go to stat, to test. We're going to arrow down to 2-sample t-test. Let's set up our null hypothesis. A null hypothesis is that our two means are the same. Our alternate hypothesis is that mu1 is less than mu2. This is our claim. Okay, 2-sample t-test. Over here we have summary stats, so you want to click on that. Our x1 bar is 189.1. Our S1 is 38.7. Our sample size is 35. Now in our second group, our X2 bar is 203.7. Our standard deviation is 39.2, and our second sample size is 28. Our alternate hypothesis is the less than symbol, which makes it a one-tail test. And then we're going to say no for pooling because sigma 1 is not assumed to be equal to sigma 2. So that's generally your default, the one you're going to pick unless it's specifically stated. Our test statistic is a t. So t is equal to negative 1.477. It's rounded to 3 decimals. Our p-value is the next one, which is 0.0725, rounded to 4 decimals. In our example, we use the degrees of freedom to be, and we use a smaller sample size, so it's 28 minus 1, so it's 27. Okay, now we look at our p-value and we compare it with our significance level, and our p-value is greater than 0.01. If the p is low, we reject the null. This p is not low, so we fail to reject the null, which means we believe the null still stands. We're going to box it and then look at our conclusion. Okay, one more thing, we want to write down the critical value And since it's a left tail test, that means we have just one critical. In order to find it, we put our alpha into the left tail. And then since it's a t-test, we're going to use the inverse t to find the critical value. So inverse t, second vars, inverse t of 0.01. We use the 27 as degrees of freedom. And over here, we end up with a critical value of negative 2.473, rounded, to 3 decimals. So inverse t, which was second vars, put in the area to the left, 0.01, and 27 degrees of freedom gives you a critical value of negative 2.4723. Rounded up, 473. When we're comparing our test statistic, the test statistic falls over to the right. It's not as negative, so it falls into that fail to reject zone. So same conclusion as before. All right, then we look at our wording. I want to go over our wording sheet. So did the original claim include the equality? No, our claim did not include equality, so we say no to that. Did we reject the null? No, we failed to reject it. So here's the wording. There is, going back here, starting here. No, it did not include it. We failed to reject it. So our wording is there's not sufficient sample evidence to support the claim. The claim. And what was our claim? And the claim was that mu1 is less than mu2, so the claim was that the treatment group is from a population with a smaller mean. From a population with a smaller mean. Okay, so there is your test, there is your conclusion, and then the final wording over here. Number 10. A test, okay, assume that a simple random sample has been selected from a normally distributed population and test the given claim. Identify the null and alternate test statistic critical values, p-values, and state the final conclusion. A test of sobriety involves measuring the subject's motor skills. 20 randomly selected sober subjects take a test, okay, it's 20, and produce a mean score of 41. With a standard deviation of 3.7. At the 0.01 level, test the claim that the true mean score for all sober subjects is equal to 35. Okay, so we have a claim that mu is equal to 35. This is the claim. Now, since it includes the equality, it's actually exactly equal to, we put it into the null. Our alternate one is the opposite, which is mu is not equal to 35. All right, so over here we have the sample standard deviation given, but we don't know what the population standard deviation is. We also have just one group over here, which means that this is a t-test. So stat, test, go down to t-test. We have summary stats given. Our null hypothesis is that mu0 is equal to 35. Our x bar is 41. Our standard deviation is 3.7. Our sample size is 20. And our alternate hypothesis is not equal to. We're going to go down and calculate over here, and we have our test statistic, which is a t-score, 7.252. Already we look at that number and we see, oh, that's a very large number. That looks like an unusual value. Okay, let's look at the p-value, which is the probability of getting such an extreme value. Over here we have 6.97 times 10 to the negative 7th. And if we're rounding this to 4 decimals, this is actually equal to 0, because you have 6 zeros before the first number. So this is a very small probability. When we compare it with 0.01, 0 is less than 0.01, which means our conclusion is when the p is low, we reject the null. So we're rejecting our null over here. We do want to find the critical value. Actually, it's values over here. We have a two-tail test, which means we're going to take our significance level, our 0.01, split it in half, and stick half into each tail. The t-distribution, the student t-distribution is symmetric, so if I'm finding the one on the left, I know what the positive one is, just has the opposite sign. Since it's a t-test, we're using inverse t of 0.005. So let's go to second vars, arrow down to inverse t, and put in an area of 0.005. Degrees of freedom is 1 minus the sample size, so that is 19. And hit enter. And we have a value of negative 2.861 when rounded to 3 decimals. So plus or minus 2.861. So we have that symmetry, which means when we have the negative one, the positive one is the same absolute value, just opposite sign. All right, let's look at our conclusion. Our original claim did include equality over here, so yes, the answer is yes. When it says did you reject it, we said yes, we rejected it. So we are up here, which says there's sufficient evidence to warrant rejection of the claim. So there's sufficient evidence to warrant rejection of the claim. That the true mean score for all sober subjects is equal to 35. Okay. That is number 10. Now looking at number 11. Okay, so we're going to test the given claim about the means of two populations. Assume that two dependent samples have been randomly selected from a normally distributed population. The table shows the weights of 7 subjects before and after following a particular diet for 2 months. We actually went through this problem in class. We're going to put this into list 1, this one into list 2, and then we're going to calculate the difference. So our difference is going to be equal to L1 minus L2, and we put that into list 3. So let's do that. Stat, edit. We're going to clear out list 1. We're going to put in these numbers. The before numbers 175, 174, 170, 196, 167, 190, 184. Aaron over here, we have 168, 165, 168, 201, 153, 192, and 172. Okay. Make sure these numbers match up. Okay, now we're going to arrow to the top, highlight L3. We're going to say L3 is L1 minus L2. And we do that by going second 1 minus second 2. And you see on the bottom here it says L3 is equal to L1 minus L2. When you hit enter, it finds the differences. Okay, alpha is 0.01. Test the claim that the diet is effective in reducing weight. So what we do is when we have dependent data, we actually do a t-test based on the differences. So we're going to do a t-test based on list 3. Our null hypothesis is always that the mu of the differences is equal to 0, meaning there's no effect. Our alternate hypothesis is our claim, and we want to have these mu differences be greater than 0. Because if you're you start at 175 and you lose, or you go down to 168 and you subtract these two numbers, you actually have a difference of 7 pounds, which is a desirable outcome. You want to have a positive weight loss. So that's your alternate hypothesis, which is also the claim. Okay, now we do a t-test based on that. So I'm going to error out of here. We go to stat, test, t-test. We're going to use our data this time. Our null hypothesis is that mu 0 is equal to 0. That's just our mu difference. Our list is L3. Our frequencies are 1. Our alternate hypothesis is the greater than symbol. And then we're going to go down and calculate. Here's our test statistic. So t is equal to 1.954 rounded to 3 decimals. P-value is equal to 0.0493 rounded to 4 decimals. The p-value is greater than 0.01. When the p is low, we reject the null, but this one is greater. So our conclusion is to fail to reject it. Now we're also going to find the critical value. It is a right tail test over here, so we just have one positive value. We're going to graph it over here. Right tail means we have our alpha in the right tail. It is a t-test, which means we're going to use the inverse t. And since the inverse t uses area to the left, we're going to use the area over here, which is 0.99. So stat, test, oh, hold on, inverse t, sorry. Second vars, go down to inverse t, put in an area of 0.99. Our degrees of freedom, well, we look at how many pairs we have. So we have 1, 2, 3, 4, 5, 6, 7. Our sample size is 7, which means our degrees of freedom is 6. So we're going to put 6 degrees of freedom, paste, hit enter. And our critical value is 3.143. So this is 3.143. Our test statistic is not quite as big, so it falls into the fail to reject zone. Okay, let's look at our wording. Fail to reject, which means we really think that there's really not a big difference over here. So let's go back to our wording. It says, does the original claim include equality? And the answer is no. So we're down here. Did we reject the null? No, we failed to reject it. So we're down here. There's not sufficient evidence, sample evidence to support the claim. So we don't think this diet is actually effective. So there is not sufficient sample evidence to support the claim that the diet is effective. Okay. So that's our conclusion over here. The next question we're actually going to skip because we did not cover this. So let's move on to the last page. We're also going to skip number 13. Move on to number 14. So number 14 over here. We're going to test the hypothesis, assume that the samples are independent and then that they have been randomly selected. 7 of 8,500 people vaccinated against the disease later developed the disease. So it looks like our X1 is 7 and our sample size is 8,500. So this is the vaccine group. On the other hand, we have 18 of 10,000 people vaccinated with a placebo. So we have the placebo group over here. So X2 is equal to 18. And our second sample size, 18 of 10,000, with the placebo later developed the disease. Test the claim that the vaccine is effective in lowering the incidence of the disease. Use a significance level of 0.02. So what are we comparing over here? Well, we have success rates. So we have the number of people who developed the disease. So that's our success. And comparing it in two groups. So we are looking at two proportions. So this is proportion 1, this is proportion 2. And we want to know if the vaccine group has a lower incident rate. So the proportion should be smaller over here. So our null hypothesis is that these two proportions are equal. Our alternate hypothesis is that P1 is less than P2. So we have two proportion z-test. We're testing proportions, which is always a z-test. And since we were comparing two different ones, it's a two proportion z-test. So we're going to go to stat, go to test. We're going to arrow down to two proportion z-test. Our X1 is 7. Our N1 is 8,500. Our X2 is 18. Our N2 is 10,000. Our alternate hypothesis is P1 is less than P2, and then we hit calculate. Here are our test statistic, which is a z-score of negative 1.80, 2 decimals, right? That's our test statistic. Our p-value is 0.0358. So this is rounded to 4 decimals, and we'll compare that with our significance level of 0.02. Well, it's greater than 0.02. When the p is low, we reject the null. This p is not low, so we fail to reject the null. It is a left tail test, so when we look for the critical values, we're going to have the area to the left. We put our alpha in that area. We use the inverse norm, since it's a z-score of 0.02. And that is second var's inverse norm of 0.02. And we have a critical value of negative 2.05. Rounded to 2 decimals. So that's our critical value. It's a left tail test, so you only have one negative value. Okay. So we fail to reject the null. This is negative 2.05. Negative 1.8 actually falls into the fail to reject zone. So same conclusion. We fail to reject the null, which means we believe that these two proportions are actually the same. So what is our final conclusion? Well, let's go back. Did our claim include equality? And no, it did not. Did we reject the null? No, we failed to reject. So it did not include the equality. So we're down here. And we failed to reject the null, so it says there's not sufficient sample evidence to support the claim. So there is not sufficient evidence to support the claim, and I'm kind of running out of room, so I'm just gonna kind of box this and have you guys fill in the rest. What is the claim? Well, the claim is that this vaccine is effective in lowering the incidence of the disease. So there's not sufficient evidence to support the claim that the vaccine is effective in lowering incidence of the disease. So you can fill this in. Sorry, I ran out of room over here. Okay, just a couple more questions. This one, the library is to be given 5 books as a gift. The books will be selected from a list of 20 titles. If each book is selected must have a different title, how many possible selections are there? Now, when they look at the 5 books they're getting, it doesn't matter which order they get it. So order does not matter in this case. The library only cares which books they get. So since that is the case, it is a combination problem. So it's the combination. We have 20 items to choose from, and we're picking 5. And sometimes you see it like this, 20 choose 5 over here. And the way we get to our combination and also the permutation is by clicking on the math button over here. Then you're going to arrow over to probability, and then you go down to the NCR, which is the combination. And okay, so you actually have to enter in N first. So put in 20, go to math, arrow to probability, go to NCR, and then put the number of items you're choosing. And this is equal to 15,504. And then the last question is 5 permutation 4. So in how many ways can you permutate 4 items chosen out of 5? And this time permutation means order matters. So we put the N in first, we go to math, probability, NPR, and we're going to choose 4. So 5 P4 is equal to 120. This is actually the same as we're picking 4. We have 5 choices for the first, 4 for the second, and so on. You can verify this is 20 times 3, which is 60, times 2 is 120. I wanted you guys to go back to the Chapter 8 worksheet as well. Make sure you're familiar with that, and let me know if you have any questions. But that concludes our review for the exam. Hope you guys are all going to do really well. Thanks.